Yeah, thank you for the introduction. That's me, Felix, understanding and supporting debugging workflows in CAD, where CAD stands for computer-aided design. And CAD can mean many different things to different communities, but in our case, we are interested in 3D models. And here's an example that we found in a public repository of CAD models, where a user has created a custom magnifying glass holder for their tool shelf. And this CAD model has been created in a dedicated software, here Onshape, for example. And the usual workflow for creating these models is to start out by creating planar sketches out of simple primitives, such as rectangles and circles. And these sketches can then be used by other operations to create or modify 3D geometry, as for example, these extrude operations. During this process, the user implicitly creates a list of constructive parametric operations. Each of them takes input arguments, which are either geometric entities, such as the face of the sketch, or scalar design parameters. Through a software engineering lens, we can consider these operations as function calls and this entire modeling sequence as a CAD program. CAD programs are useful because they allow you to change intermediate design decisions, do an edit, and all downstream operations will be automatically updated. However, sometimes these automatic updates don't work out as expected. In this example, the original author of the model changed the dimensions of the sketch rectangle, which somehow splits this part into two parts of different colors, and there are now several holes in the model. And we can see that we even have execution errors in our CAD program. So let's have a look at why this is happening. CAD operations take as input existing geometry. Here, the extrude operation uses several of these colored sketch regions, and we call these arrows references. However, after the edit, the intersections between sketch primitives have changed, and we end up with a different set of colored regions. We call this a change in topology. Now, this means that the same extrude operation after the edit has to decide which new entities to extrude. And we can see in the bottom row that the result is qualitatively different because the extruded plate does not have two circular holes, which are needed later on in the modeling sequence. And for the dashed circular hole, the extrude operation would also need to include the purple rectangular region. But in order to select this purple rectangle, we would need to know that it is semantically equivalent to the yellow rectangle. And this process of matching geometric entities is called entity matching. However, entity matching is an ill-posed problem for which we have algorithms which are based on heuristics. And these algorithms often do yield good results. Here, for example, this green rectangle at the bottom has been matched with the two rectangles at the top. But of course, sometimes they don't succeed, and this is when we have complicated reference problems. And these problems are extremely common. Since the 90s, it's a well-known issue, and people are working around it by developing resilient CAD modeling approaches or just by rebuilding a model from scratch if they can't figure out what went wrong. And in the dataset of modeling histories that we have collected for this work, 75% of all error messages were directly linked to reference errors. In terms of related work, Martha and colleagues aim at synthesizing better reference programs, which users can interact with in a hybrid fashion with both the GUI and actual code. And Cascavel and colleagues propose a new domain-specific language where reference changes are handled smoothly and robustly at the expense of upfront coding effort from the user. Their solution is entirely programming-based, much like OpenSCAD, which we saw in the first talk. Different from these hybrid and purely text approaches, we think that the current GUI paradigm works well in most cases, which is why we want to stay close to it. Now, confronted with these kinds of reference errors, users will usually have to find out what changed in their program by regenerating different model steps in this timeline and to switch back and forth to see how the program worked before and after the edit. And since we are working with CAD programs, this process is similar to debugging, let's say, a Python program, by only using print and exit statements. And this program here is quite short, and we can find the source of the error after only a few iterations. And now it looks nice again. However, this can get much more difficult for longer programs. So let's take as a new example this 3D model here, which comes from the same public repository as before. This model is inspired by a sliding camera dolly, and we will focus on an edit in this upper part. The corresponding CAD program has over 300 operations, which is extremely long, During the modeling process, the original author of the model decided at one point to modify an intermediate sketch, and this edit causes errors some 49 operations later in the sequence, which would be extremely difficult to just go through. And so what happened here is similar to the previous example. This edit in sketch 69 that we have here on the left changes the dimensions of a rectangle, which divides a circle into two parts, causing a topological change. Then a downstream operation somewhere in the middle, extrude 138, is creating unintended geometry, but it doesn't really break itself. It's only later on that sketch 75 cannot resolve its references and puts out the warning. And that's this operation which comes on 49 operations later. And the challenge in this situation is to actually find out that we have to correct the extrude operation in the middle and not the one which gives out the actual warning. So more generally, users seek to understand where they should start looking for the problem and how they should fix it. And since these reference problems are ill-posed and the user has to debug these errors anyway, we wanted to know, as a research question, what a debugger for CAD should look like. And therefore, we developed DCAD, a debugger for CAD. And DCAD is designed to answer three specific questions. First, when do topological changes happen? Second, how do we compare multiple program states with each other in CAD? And third, how do we reduce visual complexity? So let's dive into the first question. Once again, as a reminder, when you have these kinds of errors, you start by gathering information from different states of the program before and after the edit to see where unintended geometry changes happen. We look into one operation, visually inspect it, and undo the edit. And then we look into the next one, inspect it before and after the edit. And this can go on for a long time. Our tool, DCAD, is implemented as a plugin in Onshape. And the first feature that we're interested in supports this exact information gathering process. It's called the volume difference chart. And this chart replicates the timeline which we are looking at in the original GUI. For each operation, we added a scalar value, which is the geometric difference of an operation before and after the edit. And this way, the user can quickly browse this proxy information to identify suspicious operations. Here, for example, we can see that the modified sketch 69, causes a geometric difference, which we would expect. And then there's no change for a long time until the operation extrude 138. Now, a change in behavior is not necessarily a bad thing, but at least we can rule out looking into many unchanged operations. Second, once we know what operations we should look at, how do we gather more detailed program behavior information to eventually find out how to repair the model? So how do we compare multiple program states with each other? So in our case, knowing what operation could cause problems, we still might want to inspect it and remind ourselves what happened with the sketch and what happened before the edit. And what we can see by looking at user behaviors is that we are really interested in a subset of model states before and after the edit. However, with the current interface, the user has to memorize a lot of visual information, and re-executing can take a lot of time, especially for these large models. So instead of doing this, we propose in DCAD to simply roll out multiple states, which the user can then inspect in parallel. What you can see here in the top row are the model states before the edit for two operations that the user selects, and in the bottom row, you can see the states after the edit. This corresponds very much to breakpoints in your usual debugger. And this feature simplifies more detailed information gathering over multiple operations, and we can also roll out more than two operations. Finally, given these model states in this two-dimensional view, we propose visual comparison features to make it easier to track changes. So here, for example, we can directly visualize the geometric difference between the two rows by looking at the Boolean difference. And this actually corresponds to the difference from the volume difference chart. And we also propose actual reference arrows to help the user in finding these reference differences. We evaluated DCAD by performing a qualitative user study with 6 CAD experts who were already comfortable with the host CAD system, Onshape. We asked them to debug 5 erroneous edits with or without our tool. And these examples come from real-world modeling histories. We also tried this with users who were not familiar with Onshape. However, learning the actual CAD system introduced too much noise in our observations. So let us have a look at participant 1 working on task 5. Participant 1 is not allowed to use DCAD for this task, and we can observe that they spend a lot of time gathering information by passing through the CAD program and undoing the edit, so gathering information. And in the end, they did not succeed to find the error within the given time limit, which was 10 minutes, which was a frustrating process. To visualize the different model states of this observation period, we plot a staircase diagram. Here, the horizontal axis describes normalized time steps, and the vertical axis shows where we are within the modeling sequence. And there are also two different colors. All pink states correspond to program evaluations before the edit, and the green ones correspond to the ones after the edit. Overall, participant 1 is investing a lot of effort, much of it looking at unnecessary operations. And in particular, we can observe 3 main ranges that they inspected. First, this operation at the top corresponds to the fully executed model. And here we have a lot of back and forth between the two colors because the participant tried to understand global geometric changes. They're also spending some time inspecting the operations surrounding the first failed operations. And we can see some ramp-up inspections leading up to that operation. And finally, we can observe an exploration phase around the operation where the actual edit has been made and where also the actual error was lying, so which had to be corrected in the end, but which they did not find. So let's have a look at another participant, here participant 4, on the same task using DCAD. We can see that they are using the volume difference chart and the two-dimensional view, and they realize early on that some early operations seem to be unintentionally affected by the edit. And after that, they gather some more fine-grained information with features from the host system. So they're not doing everything in DCAD, which allows them to resolve the error in a very short time. Again, looking at their staircase diagram, we can see that DCAD has replaced a strongly oscillating debugging pattern with few interactions with permanent debugging representations. In particular, compared to participant 1, we can see that participant 4 has spent no time looking around the first failed operation, which is really the only message that they get from the host CAD system. They can pretty much directly enter this last phase where very fine-grained information can be obtained. Sorry, I didn't mention here, but participant 1 is on the left and participant 4 is on the right. In terms of limitations and future work, well, the main limitation of our work is actually that we are providing more information. And that comes at the risk of overwhelming users. For example, our reference arrows can sometimes be difficult to parse if an operation has too many references in the first place. And in terms of future work, we were surprised to find out that some part of our future work seems to have already started, since Onshape implemented their own repair view, their own debugger, a few months after our paper was accepted. The implementation promotes one of our core ideas, which is to simultaneously inspect different program states at once. And we are in general excited to see in which direction this feature is going with Onshape. Maybe they will adopt some of our ideas. And second, the crux of debugging reference errors comes from the fact that the CAD system is changing something without the user's consent. And during our user study, we have observed that once this trust in the CAD system has been lost, it is non-trivial to restore it and to validate that the 3D model is still working. To conclude, in this work, we tackle reference errors as a debugging problem for which we built a prototype debugger. We collected and analyzed a data set of real-world modeling histories, which informed our system design and our user study. And we hope that this information will be useful for future tool builders. And lastly, it is debatable if debugging is actually a good metaphor for solving errors in 3D modeling. Should you apply debugging to all of your problems? We don't think so. However, in the case of CAD, it actually makes sense since we are dealing with programs. Thank you for your attention.
Hi, thank you for a great talk. I'm Jotaro from Sony. I have a question on the workflow after the CAD, which is typically considered as the engineering or simulation stage. on the whole workflow. Have you ever thought about, debugging the engineering part?
Oh no, this is really just for this phase of the design workflow.
Okay.
Yeah. So we haven't spent that across yet.
Mm-hmm.
Yeah, but that's an interesting point. I think in terms of different design abstractions that we're using during design, this already brings together that geometric element and queries, these reference programs, which are synthesized for us. So there's already a link there. But then for the simulation and maybe for printing, even afterwards, that's an interesting direction to look at. Thank you.
Thank you very much.
Yeah.
Hi, thank you for the great talk. I really love it. Yuichi from SEMU. And I used to be working as a mechanical engineer before I started my PhD and using SolidWorks. So this makes so much sense, and I really like it.
Yeah.
And then the thing I was debugging at the time, using on SolidWorks, was also like assembly. Like this one is probably like sketch to parts, and then there are another thing, parts to assembly.
Yeah.
And then when it's like very big assembly, and then also like team, like everyone in the team is like working on one same assembly file, and then something happened, and like everything is broken, something. So do you have any ideas for applying this, some of the method you implement this time to assembly?
Yeah, it's a very good point. We haven't looked at the kind of errors which happen in assemblies, but so the DSLs, which are used for parametric CAD for the part constructions, and the kind of flattened, constrained DSLs which are used for assemblies, they are different in nature. And so I guess it's mostly some over-constrained assemblies or under-constrained, or maybe some intersections that you don't want to have. Is that it?
Yeah, that's usually the thing.
Yeah, that's really interesting.
Happens,
yeah, I will take that back to our collaborators, and we'll think about that. Thank you so much for the suggestion. Yeah.
Great, thank you.
Thanks.
Yeah.
Thank you for the nice talk, Karthik Ramani from Purdue. Rather than debugging CAD, CAD is very complex, which is why very few people even learn CAD. Have you thought about just supporting the various feature-based operations? There are about 15 to 20 of them, many of which you showed. Because to get to the level of debugging, you have to be pretty good at CAD, and it takes a long time, and it vanishes. It's like, it just vaporizes quickly, and then you lost your skill for a few weeks, and then you have to come back again, right?
I see.
So do you have any thoughts on if you could guide design rather than debug design?
Yeah, it's a good question. So yeah, we were, some reviewers for our paper were wondering if, for example, this two-dimensional view feature or this idea of rolling out multiple states of CAD program could be used for educational purposes, or even we started out this project by the idea of visualizing what's going on in a CAD program, as a visualization work. I think there's something that we could do with that, but there's also something nice about a tool which you can and have to master. So I'm a bit split on that, on both of these points. I think more visualizations and better explanation tools for programs, that's definitely necessary. Yeah, and I think that goes in the direction. I agree with that.
Great. We need to wrap up the session.